All right, recorded is rolling. So it is Monday, November 14th. Yeah, welcome back from a long break. We had a couple days off for hurricane, and it was Veterans Day, and then we had Saturday, Sunday. So I haven't seen you guys in a while. But you guys remember our 2-day week last week, we were going over momentum, and we also did a collision slab, and that's where we left off on Tuesday. So we need to go back and finish some stuff with momentum, which is going to be this page here. Remember, I've been using this page to as a checklist of ideas. Check. Okay. About halfway through that. Okay. And then I'll set you guys up with the lab at the in the class about last 10, 15 minutes of the class. Okay, you guys get to be bounce some balls. Got some bouncy balls back there. You're gonna measure how bouncy is the ball. Okay. But before we get to momentum, we got top scientists for energy. So this is of course last section. All right, so awesome job if you were on this list. I have not handed these quizzes back yet. I'm still waiting for a few more to come in. You guys probably know that we're at the end of quarter 3, and for teachers, grades are due tomorrow at 5 o'clock. So if you have not turned this in yet, and I have a handful of students that have it, then today's kind of like the last day, because anything you turn in tomorrow, I mean, I can't absolutely guarantee just because I'll be teaching like during the day. So like, like the official deadline is like tomorrow at 5 o'clock to get grades in. So yeah, so check all your classes, make sure you got all your stuff in, because today's a good day to get anything in that you haven't got in yet. Yeah, so quarter 3 or interim 3. That's what I meant. Sorry. Yeah, interim 3. Yeah, interim 3 is coming to a close. And actually, this the bounce ball lab, restitution lab that you guys do today. I'll have you guys turn in paper. Or, oh, hold on. Well, it's going to go on the last interim. It's going to go on the interim 4. That's what it's going on. Okay. Oh, how about the rest of this week? So I've condensed some stuff. I want to fit in because we have another huge break coming up. Of course, we got Thanksgiving break coming up at the end of this week. So yeah, I still want to get everything in this unit in before that rolls around. So here's what we no, hold on, sorry, that's touch up this thing. I'm so sorry. This is you guys. Right. So next couple of days, what way we're gonna do this is I'm gonna set you guys up in teams. You guys will be in teams with your desks, and I'll be walking around, helping you guys out, and have you guys solve the problems that I assigned to you guys, which are where's this assignment for you guys? It was this list of problems right here. Okay, so I think based on the notes that I gave you guys last week, and also that I'm about to give you guys today, you'll be able to solve all of these. Actually, there is one that might either fill you in. I think the only one that's kind of in question is number 79, which is like billiards balls, because that's like a problem in 2 dimensions. I'll tell you guys what though, I'm not going to quiz you guys on 2-dimensional because again, we got kind of a condensed unit here because we're missing a couple of days, but that's all right. We're going to make this work. But number 79 with the collisions in 2 dimensions, that is not going to be a quiz question for sure. Right. Let's see. Then on Thursdays, I still want to do an in-class quiz on Thursday. So that's coming up. But it's going to have to be open notes. So it'll be an open notes quiz. Any notes that you guys took last week, any notes to take today, any notes that you write down next couple of days, Tuesday, Wednesday. You can use any notes you take on that quiz on Thursday. Okay, and then Friday, I have another activity lined up just to take us to Thanksgiving break. And if you happen to miss Thursday for whatever reason, then that could be a makeup day for the momentum quiz. Okay, so you guys good with coming up next few days? All right. Okay, so let's break out then this page and need to go over the last couple of ideas, which again are going to be coefficient of restitution, which is like how balancing something, and also impulse, which is a change of moment method. And then I'll set you guys up with the lab in the last few minutes of class. All right, so I think the last one we left off on was like this grenade exploding. So that's not about right. Okay, here, let's do a quick recap here because I know it's been a while. We're talking about momentum. Now, momentum is just mass times velocity. So mass times velocity. This is a vector value, so directions matter. So going to the right, going to the left. Right? I have a positive versus a negative momentum. Okay? And then collisions. You care about collisions when you're applying this momentum stuff, right? And momentum is conserved. It's conserved within a closed system, which means all this mass times velocity stuff is if you add up all the bits before and after a collision, it all equates. Okay? That was like number 3, number 4. I think I solved one of those with you guys in class, right? Now, things can bounce off each other different ways. One extreme is actually perfectly inelastic, where they don't bounce off each other. Actually, I have a live demo for you guys. It's this right here. Boom. There it is. There's perfectly inelastic. It doesn't bounce at all. It sticks. Okay. And if that's true, you can just modify that original equation a little bit, and you get something looks like this. Right? One giant mass, post collision, common final velocity. That's like number 5. We solved that last week. Right? You guys remember that? Okay. The other. Oh, and you know what too is if you take this and run this in reverse, it would look a lot like a grenade exploding, which was also number 6. Number 6 was the grenade explodes. I also played you guys remember that Magic School Bus clip, right? Girl throws the ball, if you get kicked back the other way, how fast, right? Well, if you run that film in reverse, it looks a lot like a perfectly inelastic collision. So you can use the same physics. It's just like going from this state to this state, right? And then just this reverse, and that's how we solve number 6. Okay. All right, now let's move on to the other extreme kind of collision you can have, which is like perfectly bouncy, like perfectly elastic, right? So not only is momentum conserved, which is true for all these collisions, but also kinetic energy happens to be conserved. So let me do a live demo for you guys. Now it's hard to get this one exactly, but here's probably as close as I can get it. Right? It's something like that. Right? That's probably about as bouncy as you can see. That's probably pretty close to this perfectly elastic scenario. And if you have momentum is conserved, which is always true for a closed system, and also kinetic energy is conserved, which is specifically true for this type of collision, and you run this as a system of equations, then this right here is always the result of that system of equations. Okay. Now this probably right, this expression right here, not in a lot of physics textbooks, also really hard to find on the internet. So if you guys like, take physics in college, live you guys will one day, and you're asked to solve for elastic collision. Probably a good idea to have this expression on hand. It'll save you a lot of time and a lot of paper. Okay, because this is a general solution. Let's go ahead and apply this to number 7, right? Which is perfectly elastic. So head-on collision, bam. Okay. What's going to be the result? Okay, so here I'm just gonna copy paste this expression right down here. So this is for number 7. Okay. You guys know the picture. It's like 2 objects like colliding head on, bam, like that. Okay. So velocity of object A post collision, that's what final is in this context, right? Post collision is equal to, it's a big old fraction. You got velocity of object A before the collision, right? VA initial, times the difference in masses, MA minus MB, okay, plus 2 times the other mass B, times its pre-collision velocity. So these are all vectors, so direction doesn't matter. Right? All divided by the sum of the masses. Just like that. That'd be true. Okay. Well, I mean, you could check me on those. You could run a bunch of numbers, but this solution will always satisfy, again, each of these. Okay. In combination with each other. Okay. So on number 7, I gave you guys some numbers. I said, let's call mass A 1 kilogram and mass B 2 kilograms. So here's 1 kilogram. Here's 2 kilograms. Okay, and then also it's just up here, 1 kilogram. 2 kilograms. That was 2 kg. And 2 kg. Right, just like that. Okay. I told you that object A was coming in at 5 meters per second to the right, and object B was 3 meters per second to the left. And you know it's opposite direction because I called it a negative value. Okay, these are all vector values. So let's plug that in. I got what's that? Oops, lost my spot. 5 meters per second. And this guy was -3 meters per second. If you want to get it right, make sure you have a negative sign there, right? So you got to keep track of the negative numbers. Okay. So if you feed all this into this expression, then you can figure out what is the like the rebound velocity of object A. Right? You guys can see it. You guys see that? So object A post collision velocity is Let's try this out. So we do 5 times 1 minus 2 plus 2 times 2 times negative 3. And that's all divided by 1 plus 2. Okay, I'm getting negative 5.67. The unit is going to be meters per second. All the kilograms going to cancel. So that is how fast object A rebounds Boing, from that collision. Okay. Which is one of the answer choices, so we're good to go. Okay. Now, we've answered everything about that collision except for one thing. There's one thing that's sort of unanswered, which is, well, what is the post-collision velocity of object B? Like, what about the thing that's rebounding off of? Right, that bounces off and does something too. Right, and there's a few ways you can go about and solve it. Right, one way you can solve it. Here, I'll show you guys three different ways to solve this. One way is you can take the answer from this, which tells you something about object A post collision, okay? And you can go back to just general conservation of momentum. And now you know everything except for object B post collision, so you can just solve for this. This would be one unknown at this point because we just solved this. Okay. Another way is, well, you could actually do this because this is also true. So you could just plug in all these numbers and solve for BB from here, right? Of course, you'll get the same answer because these are system of equations, this result, okay? And the third way you can do it is you can just change the definition of what's object A and what's object B, right? So everywhere, all these subscripts, wherever you see an A and a B, you can just replace them. So you do BB final equals BB initial times mass B minus mass A, you know, and so on down the line, right? Just change what's the definition of A and B, right? So there you go. There's 3 different ways you can get the post-collision velocity of object B and therefore have all the information about the collision, right? Is that okay? Right. These next questions, number 8, number 9, go together because they both talk about coefficient of restitution. Now, this is a way you can measure how bouncy is something. Right? Now, how bouncy is an object? Well, it's really like 2 things bouncing off each other, right? Kind of like a coefficient of friction was between 2 surfaces. You have to know both materials, right? But coefficient of restitution, all right. So it'd be like a bouncy ball off a tile floor or something like that. Right? Now, there's sort of like a definitional approach, which is what I'm going to do for number 8. Here, just flash this up with you guys. Okay, so you got 2 objects coming in, you got boing, right, bounce off each other. Now, there's a different. Here, there we go. So coefficient of restitution is the you guys know this delta could represent difference possibly. I mean, sometimes it represents change, but here I'm trying to represent like difference of velocities pre-collision, or sorry, post-collision versus pre-collision, and then you divide those out. Okay, so well, we're about to run some numbers, but you guys see that there could be a difference in velocities before, difference in velocities after. And in fact, there's a direction change. You have to keep track of that too. Okay, but let's talk about that. Now, this will naturally always come out to a negative number, so I slap some absolute value bars on it. Okay. Some textbooks, slap a negative sign, so that negative of a negative always makes a positive number. Or here's another thing you can do is you can swap some subscripts. Because look at this, I do B minus A final to get a post-collision difference of velocities final. Right? But then you see in the denominator I just did A minus B. So it's B minus A on top with A minus B on the bottom. Right? So that's another way you can take it. What would be a negative fraction, just turn it to positive, right? Switches the sign. So this will always be a positive value. Right? So let's try this for the numbers we give you. You can add a little bit of context to this. So number 7, coefficient of restitution is this big old fraction. Velocity B post collision minus velocity A post collision, right? Difference velocities after the collision, and then compared to velocity A pre-collision minus velocity B pre-collision. Yeah, so I'm setting up with the switch subscript thing, right? So B minus A on top, B minus B on the bottom. Right. So notice that on this one, also, I never gave you the masses of these objects because that's not actually part of this the setup. Right? Like if you bounce a ball off the floor, it's like, well, one object could be the ball, you get the mass of that, but what's the other object? What's the mass of the floor? Maybe it's like mass of the entire Earth, right? Okay, so at that point, it doesn't matter, right? So anyway, the masses end up not really factoring into this definition, with the changes in velocities and the whole deal. But I gave you guys velocity B post collision was, well, I'm going to make up my own numbers about that. Okay. Let's say, I have a picture down here. So whatever these are, object A, object B. Okay. Let's say this guy's coming in at like 5 meters per second, and this guy's coming in at like 3 meters per second, but the opposite direction. So I'll specify that with a negative sign. Okay. And they're gonna bam, bounce off each other, and let's say a rebound kind of like this. So object A post collision is like -1 meter per second, and object B is like I don't know, like +2 meters per second. Right. There's some combination of masses that could make that work out. Okay. Right. So let's feed those numbers into this expression. Right. Now, post collision is like this down here. Guys, what is the difference between +2 and -1? 3. It is 3. You guys see that? Right, like you put this on a number line, right? But here's 0. Here's +2. Here's -1. You guys see the difference? There's going to be 3, right? So we have down here -1 minus +2. Well, okay. I guess not negative over negative, but still good, right? So the difference is like 3 units, right? Okay. This would be meters per second. Okay. Okay. How about pre-collision? So if you do B minus A, I'm so sorry, I'm messing up everything. I meant to put that in the post-collision. I was trying to do post over pre. Oops. Right. Let's look at this strategy. Let's try this again. Coefficient restitution is, I'll just feed the numbers in here. How about that? Okay. So I got -1 meter per second minus +2 meters per second. Okay, just like -3. Okay. And then pre-collision. Now I'm doing B minus A for pre-collision. Starting again. It's been a long weekend. It is a Monday. Use that as my excuse. How about that? Okay. Sorry. Okay. So post collision on top. Okay. B minus A. Okay. So I'm doing 2 minus -1. There we go. 2 minus -1. Okay. Meter per second. Okay. So there's my 3 units change. Okay. Okay. Then pre-collision. So before the collision. Okay, I'm doing A minus B here. That's 5 minus -3. Guys, what is 5 minus -3? I see it's going to be 8. Yeah. The difference between +5 and -3 is 8. You see that? Okay. So isn't this like 3 meters per second on top, 8 meters per second on the bottom? Okay. Okay, so that'd be coefficient restitution of like 0.375. Right, about 0.37. Right. So okay, you could change out the masses of these objects, but if they're like the same materials, then you would expect this to be the case, right? Even if you throw them at each other at different speeds, you would still expect them to bounce off each other with this proportion, right? So the post-collision difference in velocities would be about 37% of the pre-collision difference in velocities. Okay, you guys see that? Okay. Now, coefficient restitution is going to be bounded between 2 numbers. Okay. Here's one extreme condition you can have. Okay. Guys, what's the post-collision difference in velocities between this object and like the entire Earth? Be 0, right? Okay. So the numerator would just be 0, and the denominators, like however fast this was about to collide. So 0 divided by some number is just going to be 0, right? Okay. And that is called perfectly inelastic. Right? That's exactly what that is. Okay. But the other extreme you could have would be this right here, where the post-collision difference of velocities is the pre-collision difference of velocities, right? Because in this case, like one transfers entirely to the other, right? And so regardless of what the numbers are, if you divide them out, it's going to be what ratio? Like 3/3, 7/7, but like a 1-to-1 ratio, right? So that'll be like perfectly elastic. Right, is that okay? And then the example I did, well, kind of a realistic example because it's somewhere between those two, right? Here's that. Yeah. Yeah. All right, you guys good there? We good? All right, now there is an alternate way to approach coefficient restitution. If one of your objects is like the earth or the floor, it's actually what I'm going to have you guys do in your lab today. Okay. So you guys know, and this is also what we're about to do, number 9. Right, number 9. Okay. Like if you bounce a ball off the floor. So here's the floor. Okay. You have some ball, some mouse, whatever. Okay. And boing. Right, do something like this. Let's say it's pretty much vertical. So maybe like horizontally, it's like a time axis, basically, right? Okay. So I see a drop height here. I'll call this capital H, but maybe I'll throw in a subscript just to emphasize that it's definitely drop height. So drop height, right? And it's going to rebound to some shorter height. And I'll call it like lowercase h. And I'll call this rebound. Right. Okay, so now, if you just know what those heights are, the coefficient restitution is like a couple steps away. It's like embedded in this information. Right? Because remember what coefficient restitution is really defined as. It's what's this rebound speed, V rebound, compared to this V crash, that crash speed. Is that true? Right? You see how there's a direction change, right? So for example, what if the rebound speed is like 7 meters per second and the crash speed is like 10 meters per second? What if that was the case? What if V rebound is like 7 meters per second and V crash was like 10 meters per second? Okay. Now, also the fact that there is a direction change, I have to apply a negative sign somewhere. So maybe we'll call up negative. Okay. But remember, coefficient restitution is, you take the ratio of these two, but then make it negative so it comes out to be a positive ratio, right? So what would it be for this exact scenario that I just did right here? 7 over 10, which is like 0.7. Guess that? That would be coefficient restitution for the scenario. Is that true? Okay. But those crash and rebound speeds are related to the drop and rebound heights. Right? Do you guys remember what that relationship is? What is V as say as an expression of as a function of like the drop height? You guys saw this like kinematic motion. You guys saw this conservation of energy. Galileo drops a ball off the Leaning Tower of some height. And how fast did it crash onto the ground? It was square root of what? 2gh. You guys remember that? Square root 2gh. Right. Right. So you guys have seen this in multiple contexts before this class. All the way back to kinematic motion, one of the first things we did is third kinematic formula, start from rest. Okay. You see the final is going to be square root 2ax, which is like square root 2gh. Right. Or if you do conservation of energy from potential to kinetic energy, right, you still get this expression. Right. So what if my drop and rebound heights are like 100 centimeters, 100 centimeters, and let's say like 49 centimeters, something like that. Okay. You could run this. You could calculate each speed individually, and you could like crunch all the numbers. Right? Or how about this? Okay. What if you did the ratios of the velocities, V rebound compared to V crash, is equal to the square root of 2g h rebound over square root 2g h drop, and that also be equivalent to that. Is that true? Okay. Hey, what's going to cancel out? Yeah. So couldn't coefficient restitution just be the square root of the ratios of the heights? Right? Isn't that true? Right. And then if you run the numbers, what's the square root of 49 on 100? It's still 0.7. Right. Okay, so, and this is a unitless ratio, right? So, by the way, these speeds don't line up exactly with these drop heights, but it did make the coefficient restitution come out the same. Okay. Well, I guess this would be true for some planet. There's some planet out there in the giant galaxy that this would be exactly true for, right? But not Earth. Okay. Right. You guys get that? Okay, so let's apply that to number 9. Right. So I got coefficient of restitution is the square root of rebound height to drop height. Okay. And I gave you guys a rebound height of like so many meters and a drop height of so many meters. Or you could do centimeters and centimeters, like whatever you measure in, as long as you're consistent in the units, everything still cancels out, right? Okay. So is that I'm looking like this for coefficient restitution. Pretty sure. Or I think you guys have different numbers than I do, but that's how you would solve that, right? Right. You guys good there? Okay. Right. So yeah, so if you bounce a ball off the floor, as long as you drop it, right, start from rest. Right, what is the drop height? What is the rebound height? Take the ratio and then take the square root. That will tell you like how bouncy it is coefficient of restitution, which is again like the ratio of the difference in post-collision to pre-collision velocities of the two surfaces. All right, that goes. All right, so definitely hold on to that idea because I'm gonna set you guys up with the lab the last few minutes of class today. All right, last 2 minutes. But there's one more concept I need to throw at you guys. Okay. So I have a poster that looks pretty similar to this, which is like a force versus time. If you apply force for some time, then you get what's called an impulse, like a change in momentum. Okay? And it could be the area under the curve, like the area that light gray triangle. Okay? But you can also take like the average height, right? But the average force in this case, right? Average height of the graph is the average force. Okay. And then times the time interval. Time interval I'm calling delta t. You guys see delta t could be time interval, right? And you guys see it's a darker green rectangle, but see how that darker green rectangle and the bright green triangle have the same area? Okay, that's the same impulse, delta p. Impulse. Okay, let me write this down for you guys here. Right. So if you have impulse is a change in momentum. Okay. And in physics, you write that as delta p, like a change in momentum, right? Now, p, you guys remember momentum is mass times velocity. So if you're changing momentum, you have a mass times a change in velocity. Yeah. You could have a changing mass. I don't think I'm ever going to throw you guys a question like that, but in general, you could, like if you have a conveyor belt and you're like throwing like objects on the conveyor belt as it's moving, you want to say, well, what force you have to apply to keep it going at constant velocity. You could have a changing mass, so it wouldn't be exactly what I wrote here, but yeah, most physics problems, you're throwing it this way. You have a constant mass and a changing velocity. But hey, changing velocity, you guys know that there's an acceleration involved. If there's an acceleration, there must be a what applied? A force, right? So this is a force for some time interval. Okay, and really this is an average force. Okay, because a lot of collisions realistically, like here, the example we're about to go through, the story we're about to go through is like a bat hitting a ball. But if the bat hits a ball, is it true that like, here comes the ball, here's the bat? Right? That if you had like slow motion, that they would start to make contact, and then the bat pushes more and more against the ball, and then the ball starts to change direction and then rebounds off the bat. Right? Now that process takes a tiny fraction of a second, but that force would be variable. Actually, it would probably look pretty similar to this graph, where it's like a triangle-shaped graph, where it builds up and then goes away, and then the ball loses contact with the bat here. Right? But if we run like this type formula, this force that we're solving for is actually this average force, which is like halfway here. Okay, I said that's how this lines up. And so let's run some numbers. Here's what I do just to save us a hot minute. Number 10, number 11 are very similar questions. If you can do one, you can do the other. So I'm just going to do number 11 with you guys. Number 11. So number 11, I asked you to solve for the average force given everything else. Suppose there's a baseball. Number 10 and number 11 both involve a bat hitting a ball. So here's your baseball. Suppose the change of velocity is like, well, my paper says 41 meters per second. Now, change of velocity, the ball might be on a tee and be hit off at 41 meters per second. So 0 to 41, that would definitely be a change of 41. But what if the ball is like thrown at 10 meters per second to the left and it's hit back at 31 meters per second? Guys, what is the difference between 10 to the left and 31 to the right? 41. Like, is that so? This is kind of ambiguous. This could be a lot of different situations. Right? Just gave you guys two. Right? We're solving for the average force and this collision happens over a tiny, tiny fraction of a second, maybe like this many seconds, for example. You guys see the one algebra step? You guys can take the time interval and divide it down here. Okay. So, meant to say something about that to you, but I won't here in a minute. Okay. So if you just divide down the time interval, you get 0.15 kilograms times 41 meters per second change in velocity, right? That's some change. Okay. Divided by the time interval, I'm getting this many newtons of force. Now, again, that's an average force from the bat on the ball. Okay. The maximum is probably about double that, but that could be like the average force. Okay. You guys get that? You know what else I mentioned? I can fit it in this space right down here. Is if I solve for the force in general, so in terms of variables, I'm going to get mass times change of velocity, all divided by change in time. Isn't that kind of what we just did? Okay. Hey, look at this. Force equals mass times, well, what is rate change of velocity called? What's that called in physics? Acceleration? Is this F equals ma? Hey, that's Newton's what law of motion? It's Newton's second law of motion. You guys see that? You guys see how the impulse formula is just one step away from Newton's second law of motion? Right? That's actually how Newton thought about his own second law of motion. He said, oh, if you apply a push or a pull to something, it's going to result in a rate change of its momentum. Okay. You guys got that? All right. So we got oh, yeah, we got plenty of time. We got a solid what, like 60, 50 minutes here, 50 minutes. Okay, this is perfect. Right. So you guys remember this page that I handed out to you guys back in the day? Right. On the opposite side, I printed out for you guys. Well, really only need like half this paper. This lab that we're going to do today. You don't have to fill out the whole table, but fill, at least 2 or 3 rows. Okay, go for that. So here, I'll guide you guys through it. So back in the lab area are a bunch of bouncy balls and a bunch of meter sticks. And you can do this entire lab by just picking out one bouncy ball. So pick this guy, for example. Let me do this one. This one's better. Okay. And measuring what is the drop height and what's the rebound height using the meter stick. Okay. And you can calculate the coefficient of restitution, which is the physics way of saying like how bouncy is the ball. So let's go through this table here. Right. Yeah, you can choose different drop heights and measure different rebound heights, right? But I bet that regardless of the drop height, rebound height, if you use the same ball, the ratio of those two, which is what this third column is, the ratio, should be pretty consistent all the way down. Maybe changes a little bit, but it should be pretty much, might be the exact same number all the way down. Okay. But finally, take the square root. Can you guys take the square root of that ratio? And that will tell you the coefficient of restitution. Right? Is that okay? Okay. You know what? Just to save a minute here, because I know we're missing a couple of days, so normally I'd give you guys a bit more time. But if you graphed, here, I'll do the graph with you guys. If you guys did the rebound height compared to the drop height, and I told you guys that the ratio of those two should be the same, therefore the square root will also be the same, right? What do you guys think this graph should look like? Should it look like that? Maybe you get something kind of like points of data look kind of like that. Should line up a linear relationship. Okay, so you guys don't have to do the graph. That's what the graph would look like. But figure out what's the coefficient of restitution for some bouncy ball. Okay, right, yeah. Yeah, I got an extra for you guys. Right, so yeah, you guys got the rest of the class to do this. I know this is on your results printed on your homework paper, so I'll have you guys just go ahead and turn in this lab with your homework because it's all on the same paper, and then I'll put this all on the fourth or interim. All right, and that is a wrap on the recording. I'll walk around and help you guys out on the lab.